Hey everyone, today we're going to crack the code on a really important calculus concept, differentiability. Now, I know it sounds like a super complicated word, right? But at its heart, it's all about one simple idea. Is a graph smooth, or does it have sharp pointy corners? Let's dive in.
Okay, picture this. You're on a skateboard. Would you rather cruise down a nice, smooth ramp or try to ride down a jarring staircase? Obvious choice, right? Well, it turns out calculus is a lot like a skateboarder. It really prefers the smooth ramp. And in this explainer, we're going to see exactly why. So let's get this straight from the very beginning. Whenever you hear a mathematician say a function is differentiable, I want you to just translate that in your head to the word smooth. That's all it is. A smooth graph has no weird breaks, no sudden jumps, and, this is the big one, absolutely no sharp corners. So what does smooth really mean in math terms? Well, it means that for any point on that curve, literally any point you pick, you can draw one and only one perfect tangent line. And that line, that tangent, tells you the exact slope or the instantaneous rate of change right at that specific spot. It's perfectly clear.
Okay, now this brings us to a huge myth, a classic trap that so many students fall into. You might think, hey, if I can draw the entire graph without lifting my pen, that means it's continuous, so it must be smooth everywhere, right? Well, is that actually true? Let's investigate.
Let's put two functions head to head. First up, good old f of x equals x squared. This gives us that nice, familiar, smooth U-shaped parabola. It's continuous and, yep, it's differentiable everywhere. No problems here. But now let's look at the culprit, f of x equals absolute value, the absolute value function. It creates this very sharp V shape. Now look, you can still draw it without lifting your pen, so it's definitely continuous, but what about that pointy bit at the bottom, right at x equals 0? Something seems a little off there, doesn't it?
Let's use a gaming analogy. A continuous path in a game just means there are no gaps or holes you can fall into. You can keep on walking. But a differentiable path, that's a path that's also smooth. There are no sudden 90-degree turns where you have to slam on the brakes and totally change your direction. That V-shape is exactly like hitting a sharp corner in a racing game. You can't smoothly drift around it, you have to make an abrupt turn.
And there we have it. Myth busted. A function can absolutely be continuous at a point, but not be differentiable there. And our absolute value function, f of x equals x, is the ultimate proof. It's connected everywhere, but that sharp point at the bottom is a no-go zone for differentiability.
Okay, this is great. We can see the corner with our eyes. But this is math. We need to be able to prove it. So how do we create a kind of mathematical sharp corner detector? Well, calculus gives us the perfect tools for the job. First up is something called the left-hand derivative, or LHD. Just think of it like this. You're walking along the graph from the left side, getting closer and closer to your point of interest. The LHD is like asking, hey, in the split second right before I arrive, what does the slope look like? It's the slope from the immediate left.
And as you probably guessed, if there's a left-hand derivative, there has to be a right-hand derivative, or RHD. It's the exact same idea, just from the other direction. You're approaching the point from the right, and you're measuring the slope just before you get there.
And this brings us to the golden rule. This is the big test for differentiability. For a graph to be truly smooth at a point, the slope you find when you approach from the left must be exactly the same as the slope you find when you approach from the right. LHD must equal RHD. That's it.
So let's use our new tool on our main suspect, f of x equals x, right at that sharp corner x equals 0. Step 1. We calculate the LHD. That line coming down from the left has a slope of -1. Okay. Step 2. We calculate the RHD. That line going up on the right has a slope of +1. Got it. Final step. Let's compare those two numbers.
And what do we see? Well, it's as clear as day. -1 is most definitely not equal to +1. They don't match up at all.
So, our final conclusion is simple. Since the LHD does not equal the RHD, the function f of x equals mod x is not differentiable at x equals 0. And just like that, our mathematical detector worked perfectly. We've officially proven that the sharp corner exists. All right, so we've become experts at spotting these problem points. But now it's time to level up and learn a real calculus superpower. We're going to see how to handle functions that are nested, one inside of another.
I mean, take a look at a function like sine of x squared.
This is a little tricky, isn't it? It's not just a simple sine of x, and it's not just x squared, it's a whole function x squared that's been plugged inside the sine function. How on earth are we supposed to find the derivative of something like that?
Let's think about it like a viral social media trend. You've got the original idea, the dance move. That's your inner function. Then a huge influencer comes along and does the dance. That's the outer function. They're the one who makes it go viral. The final impact, how fast the trend spreads, depends on both, right? It's the influencer's impact multiplied by the original idea's impact. The chain rule in calculus works in exactly the same way.
And here it is, the formal chain rule. It just says that the derivative of the whole nested function is the derivative of the outer function, that's our influencer, multiplied by the derivative of the inner function, that's our original idea. See how one triggers the next? It's like a chain reaction.
Let's actually apply this to sine of x squared. It's a simple step-by-step process. Step 1. Identify the functions. The outer function is sine of u, and the inner one is x squared. Step 2. Differentiate the outer. We know the derivative of sine of u is cosine of u. Step 3. Differentiate the inner. The derivative of x squared is just 2x. Step 4. Multiply them together, like the rule says. We get cosine of u times 2x. And for the final crucial step, we substitute the original inner function x squared back in for u. And there it is. Our answer is cosine of x squared times 2x. See? Not so scary when you break it down.
So let's do a super quick recap. First, differentiability is just a fancy word for smoothness. No sharp corners allowed. Second, the official test for smoothness is that the left-hand derivative must equal the right-hand derivative. Third, remember this key relationship. Being differentiable means you must be continuous, but being continuous doesn't mean you're always differentiable. And finally, we've unlocked a new superpower, the chain rule, for handling functions inside of functions.
Seriously, you should feel great about this. You've just busted a major calculus myth that confuses so many people. And you've learned one of the most powerful tools in all of calculus. That's a huge step forward, so well done. So, I'll leave you with a final thought. We've mastered functions that are inside other functions. But what happens when two functions are just being multiplied together? Or when one is divided by another? What are the rules for those situations? That's a question for next time. Thanks for watching.